We have here a transformation from R3 to R3, and we are going to verify whether this is a linear transformation or not. To do that, we need to satisfy these two conditions. The first condition is that for a specific two vectors, let's say we have here the sum of vectors x and y, okay, their sum can be or equal, just equal to, the sum of their transformation is equal, the transformation of their sum is equal to the sum of their transformation. Again, okay, this is the first condition. The transformation of their sum is equal to the sum of their transformation. Of course, we're going to define later the components of x and y vectors, but this is the first condition that should be met. The second condition pertains to a certain scalar, where we have here the transformation of the multiple. We have scalar c times, we have here vector x, okay, is just equal to the product of the same scalar and the transformation of the same vector x. Okay, so we have here these two conditions, and let's start with this. The first condition is this, but of course we're going to define the two vectors x and y with these components. Since our vectors are in the given is x sub 1, x sub 2, and x sub 3, so that's for our x sub 1, x sub 2, and x sub 3. And for y, this is simply use y sub 1, y sub 2, and y sub 3. So now let's try to show whether the transformation of the sum is equal to the sum of the transformation. But first, let's substitute the components of vectors x and y. So you have here x sub 1, x sub 2, x sub 3, plus y sub 1, y sub 2, y sub 3. And let's add them up. So your first would be x sub 1 plus y sub 1, the sub 1s. You have your x sub 2 plus y sub 2, the sub 2s. And x sub 3 plus y sub 3, the sub 3s. Now that we have this, let's start with this transformation of theirs. So again, x sub 1 is the first. So the first here is this entirety. This is our second, that's our x sub 2 in this case. And x sub 3 is our entire binomial expression here. That would mean the transformation, we have the first entity, x sub 1 plus y sub 1 minus, since it's minus, let's use parentheses, your second entry. That's just for this first here. The second, you will have your second entry or component minus the third. Again, use parentheses if possible, especially with preceded by a minus sign. Okay. And then you will have here the third minus the first. Okay, so this is now the transformation using this and these sums here. Of course, I could also write parentheses here. Now is to distribute the negative signs. So you'll have x sub 1 plus y sub 1, distribute that, minus x sub 2 minus y sub 2. Next, x sub 2 plus y sub 2, again distribute that. You will have minus x sub 3 minus y sub 3. Then x sub 3 plus y sub 3, again distribute that, minus x sub 1 minus y sub 1. Now from here, take note our goal is to show that this transformation of the sum is equal to the sum of the transformation. In short, we are going to show that there is a separate transformation for x, vector x, and there is a separate transformation for vector y. Take note that vector x composed of the x components and y will be the y components. In this case, let's try to combine the x components and the y components. You have x sub 1 minus x sub 2, right? Plus y sub 1 minus y sub 2. Second, x sub 2 minus x sub 3 plus y sub 2 minus y sub 3. Then x sub 3 minus x sub 1 plus y sub 3 minus y sub 1. Once we are done with this, of course, take note you have your x's here now, here, and here, separated by plus, plus, plus your y. Okay? So we can separate these two, this into two vectors. X sub 1 minus x sub 2. Next, x sub 2 minus x sub 3. Next, x sub 3 minus x sub 1. Then plus all the y's, y sub 1 minus y sub 2, y sub 2 minus y sub 3, and then y sub 3 minus y sub 1. Why do we do this? Because when you look at this one here, this is actually similar to our transformation, and since we're using the components of x, we can say that this first group here is just the transformation of your vector x. Similar thing, plus the second one here, or second group, is a transformation of your y. Okay? This would mean we have shown that the transformation of the sum is equal to the sum of the transformation. Hence, the first condition has been satisfied. Let's proceed to the second condition, as we are going to use c as any scalar. In short, the transformation of c times vector x can be expressed as c times the component of your vector x, x sub 1, x sub 2, x sub 3. Let's multiply these first. You have c x sub 1, c x sub 2, and c x sub 3. Once we are done with this form here, our goal is to come up with our c, or factor c. In short, let's now have their transformation. So first component minus second component, cx sub 1 minus cx sub 2. Next, cx sub 2, the second component and third component, minus cx sub 3. And then you have cx sub 3, the third component, minus your first component, minus cx sub 1. Here we can factor c in all. So you have here x sub 1 minus x sub 2, c, x sub 2 minus x sub 3, c, x sub 3 minus x sub 1. Okay, now since all components has c, we can simply take it out. Once we take out c, what's left here is x sub 1 minus x sub 2. Okay? Second, x sub 2 minus x sub 3. Then, x sub 3 minus x sub 1. This is similar to this here earlier, which is the transformation of your vector x. In short, we have c outside, transformation of your vector x. We have shown now that the transformation of c times vector x is equal to c times the transformation of vector x, and our second condition has also been satisfied. Ultimately, this transformation here is a linear transformation since we have satisfied both conditions. Thank you very much for watching.